Okay, so in the last video we introduced our notion of an inner product, and remember that that was our way of trying to generalize this Euclidean notion of if you have two vectors, v and w, then it's to ask how much of v is in the direction of w. So this is like v sub w, or projecting v onto w. And so remember to calculate that coefficient, we used inner product when we talked about decomposing vectors. And we want to use that same idea to be able to decompose functions into sums of sine and cosine series. So in this video, I'm going to introduce a new inner product, which we're going to use to compute the sort of dot product or inner product between two functions. And what this will allow us to do is, again, since the inner product is a generalization of projecting, we'll be able to project our functions onto sine and cosine series, and then eventually build the functions back up as the sum of sine and cosine series with certain coefficients. So there are a lot of geometrical notions which will come about from this. Like, for example, you'll be able to see what it means for two functions to be orthogonal, and sine and cosine functions are orthogonal in some sense with respect to this inner product. And so first I'll introduce this, and then I'll give some intuition as to some of the things that you can do with this inner product functions, and how that's similar to some of the things that you can do with Euclidean vectors. So, forewarning, before I get into this, if this construction seems a bit artificial, that's because it is. Historically what happened was Fourier was just, again, working on the heat equation, and he came up with this brilliant realization that if you just take the integral of some functions with sine and cosine functions, then you can get some coefficients out of that, and you can reconstruct your function as the sum of sine and cosines. And he didn't have any idea of all this linear algebra background that we've been covering in these videos, because the language just didn't exist back then. Later, some people came around and realized, oh, you can take some of Fourier's work and combine with linear algebra to get this nice generalized picture that you can understand things better with. And so that's what the viewpoint that we've been building up to with so far. So in this video, I want to sort of give an intermediate introduction to this inner product, which is to say that given all of the linear algebra stuff we've done so far, how might one be able to think of creating this inner product on continuous functions? So the first thing I have to talk about is the vector space again. So remember in one of the earlier videos we discussed that we can think about functions as vector spaces, and that's because you can add two functions together, or you can scale up functions, and those are still functions. So what is the vector space that we're working with over here? Well, these are both functions that are continuous on the interval 0, 1, so that's what says this, C0, 1. And so that just means that you're looking at any continuous functions on this interval. So here we have two examples of such functions, f of x and g of x. F of x is sort of a parabola shape, g of x is sort of the sinusoid shape, restricted to the interval 0, 1. And we want to somehow think about how much of g of x is in f of x. How can we project f of x onto g of x? So we don't have any immediate idea of how to do that, but one thing that we can do is sort of think of these functions maybe as a computer would. So a computer doesn't have an infinite amount of storage. It can't like keep track of the output for a function for every single real number. So what it does is it takes a discrete amount of values for the function and stores them as sort of like a vector. And then it does computations with that. So we can sort of think about approximating these functions with vectors which take up values of the function. And then we can do some calculations with that, and that'll lead us to our inner product. So what I mean by that is, say you split up the interval 0, 1 into 4 different intervals. 0 to a fourth, 1/4 to 1/2, 1/2 to 3/4, and then 3/4 to 1. And then on the right side of each interval, you take the value of the function. So you have f1 is f of 1/4, f2 is f of 1/2, and so on and so forth. And you do the same thing with g. Now we're going to encode this into two vectors. So we're going to look at, should probably write this, f1, f2, f3, f4, and we're saying that each of these coordinates sort of is a representative value of this function for that interval. And we can do the same thing for g, so g1, g2, g3, and g4. So these sort of approximate our continuous functions by giving us different values of the functions across the domain. And these vectors, however, are inside Euclidean space, right? So these are both in just R4. And we know how to take a dot product in Euclidean space, so we can just do that. And this will come out to be f1g1 plus f2g2 plus f3g3 plus f4g4. But of course, our vectors here don't completely encode all of the information of our function, right? We sort of encode an approximation, which is to say like, okay, over here, the value is approximately f1. On this interval, the value is approximately f2, and so on. So what if we took a better approximation? What if we split up into 8 intervals and said, okay, over here the value is approximately f1, here it's approximately f2, here's approximately f3, f4, f5, f6, f7, and f8. So instead, now we have a vector, f1 all the way up to f8, and another vector, g1 all the way up to g8. And both of these still approximate our functions, except they approximate it better, because we sort of get more information out of this because we can look into smaller intervals. And both of these live in R8. So we can again take their dot product, and this is just going to be equal to f1 g1 plus all the way up to f8 g8. Okay. And here, we can keep going further along. We can split up into 12 intervals, and split this up into 12 intervals, and say, hey, these look more like our function than before. So if you look at these boxes over here, they sort of approximate our function. But if you look at these boxes over here, they're very close to what our function actually represents. So maybe like this idea of taking vectors to approximate functions and taking more and more divisions is actually useful because we can get a lot of information about our function out of these approximations. So if we keep on going on with this dot product, it's pretty obvious what's going to happen. We're going to get the sum over I equals 0 to n of, or I guess I equals 1 to n, of f sub I, g sub I. So it's just saying, take the ith value here, take the ith value here, multiply them together and add them. And that's what these dot products are. So to write it a bit more explicitly, this is the sum from I equals 1 to n. And so what we're doing is we are looking at the value of, we're splitting up the interval 0, 1 into n different intervals, and we're looking at the right endpoint of those. So fi is just f of I divided by n, and gi is g of I divided by n. And so we're saying that as we increase the value of n, and we take these dot products, that sort of encodes more information about how we might want to think about projecting f onto g. Again, this doesn't have any intrinsic meaning yet, but it's sort of the idea that we want to think of this dot product as sort of being a limit of the dot products as we increase these vector approximations. Okay, so obviously you might realize that for all these values, these are, for the most part, non-zero. So if we just take the limit as n goes to infinity, then we're just adding an infinite number of non-zero values, and that's not going to converge to anything. So you might already realize that we should modify our inner product a little bit. So remember our notation for inner product is f and g. And so here, this will be the actual inner product of f of x and g of x. So our first thought was maybe we should take something like I equals 1 to n of f of I over n, g of I over n, and then if I write down, but over here you want to add a limit as n goes to infinity. But obviously this is going to diverge. So maybe what you want to do is control the size of it a little bit. And you might realize, or you might have been realizing what's been going on if you've done calculus before, that this sort of seems like the construction of the Riemann integral. And so what you do with the Riemann integral is you take the values at the points and you divide by n and then you sum everything up so that you actually get something that converges as n goes to infinity. And so to give sort of better intuition as to why we should divide by n rather than saying we do it so that converges, let's look at the case where f of x and g of x are, say, some constant functions. So if this is the value on 0, 1, and this is just a value of 2, say, and this f of x, and then g of x is going to be the value, say, 1, then we can look at our vectors that approximate these. So let's split up into 3 subintervals, and this up into 3 subintervals. So the 3 subintervals here, f1, f2, and f3, they're all going to have the value of 2. This is going to be the vector 2, 2, 2. And similarly, it's going to be the vector 1, 1, 1. And if we take the dot product of those two vectors, that's going to be 2 times 1. And then you add it up to itself 3 times. So in general, if you have like a vector of like n that approximates this function, you'll be adding 2 times 1 n times. But if we instead divide by n, since we're adding it up n times, this is going to be equal to 2 times 1. That seems fairly natural, that if you have two constant functions, then the inner product should just be the product of the values that the function takes. And so here, you might realize that this is nothing else than, again, the integral from 0 to 1 of f of x, g of x, dx. And so, to sort of recap what we're doing, this inner product, in a way, just says, hey, take the value of f of x and g of x at each point and add them all up together from 0 to 1. And we can't add them because they'll diverge, so instead we take an integral. And so how is this analogous to the Euclidean case? Well, in the Euclidean case, you're sort of saying to every direction, so for example here in R4, we have 4 basis vectors. And to each of those directions, we assign a value, f1, f2, f3, f4, and g1, g2, g3, and g4. And so the inner product here tells us multiply those corresponding values and add them all up together. And that's the same thing we're doing here. So here we have an inner product of f of x and g of x as sort of being defined by this thing. So again, there's no clear understanding of what this represents yet. And I'll go through some examples to see why this should be an actual thing. And then I'll end off the video by showing that this does satisfy the axioms of the inner product that we went over in the last video.